founder and principal of Fractal, to set the context for BIM data capture management and exploitation. Mr. Kupusami, over to you.
Afternoon. I'm going to just get straight into this. So, just to get everyone a little bit of interaction as we start off the afternoon after a big lunch. Does BIM really work? Can I get a show of hands? How many people want to go BIM works? Give me a show of hands. A handful. Not unanimous. So, my view is that after 20 years of BIM adoption, the industry still builds late, we're over budget, and we still have rework baked into the process. So BIM has given us parametric modeling, it's given us better drawings, clash detection, more standards to follow, but has it really fundamentally changed how we build? And why is that? Because BIM has become about documenting what a building looks like, not how it will actually get made. And until we shift that focus, BIM remains a digital mirror of old problems, not a pathway to new solutions. So right now, today's tools excel at documenting the final product. We're obsessed with geometry and parameters that capture basic elemental description. We focused on creating beautiful looking models on a screen, but we've missed the critical engineering intelligence that makes a building stand up in the real world. Our digital components, our Revit families today, are still relatively dumb parametric geometry. They describe the physical dimensions, in this case of the brick, but they don't contain any of the critical engineering data. This isn't just a number crunching exercise, it's about interpreting structural loads, assembly methodology, specification, and supply. The result is that this intelligence of how we build is rarely ever captured in a way that's reusable, automated, or directly actionable. The industry needs a paradigm shift. And rather than a tool for drawing buildings, we need a tool for designing how buildings actually work. What I'm proposing is that we recognize buildings as a system of systems, as parts, and defined by manufacturing rules, capturing the process, not just the product. And when codified, this logic becomes reusable, scalable, computable, and a foundation of lifecycle data that you can trust from design all the way to construction and operations. We can start to productize buildings and extract true efficiency in designing and constructing. A true DFMA digital component goes beyond geometry and materials. It encodes the knowledge of its own manufacturing and assembly needs, and it carries its own intelligence, performance parameters, thermal and compressive strength, interface, tolerance rules, sequencing, access constraints, the tools, the manpower, install rates, cost, lead time, QA and QC, all of these things, traceability. And if you can encode all of this information, then actually we have a chance to stop drawing drawings, to stop making plans, and instead to start simulating sub-assemblies, assemblies, how we make a building, automating coordination, getting accurate pricing, and buildability right from a component level up. Sounds super idealistic, I know. So this is actually really about how do we build anything, but within the intelligence of system constraints. Instead of a single monolithic model, imagine having a system of available components that can be selected and configured to meet the project solution space. This is a body of work that I've been deeply involved in, and I'll use Podium as an illustrative case to show you how these principles that I've spoken about come into practice. The answer for Podium is what we call CUBS, the Contextual Unified Building System. an open data schema that creates a golden thread of data from design through to delivery. And this is not a closed proprietary file type. It's a multi-dimensional, domain-specific object model that captures these critical relationships and dependencies across architecture, structure, and MEPF disciplines. And CUBS is also capable of connecting design logic to financial and supply chain and product data, all in that single unified data model. In Podium, buildings are visualized as 3D models, but behind the scenes, they live in CUBS, represented as a graph where every element, its attributes, its relationships, are all connected and all consumable. And now let's look at what we can do when we've captured all of this information within a platform. This new data model can be made practical and is already in use. Design agents automate, generate, and configure designs which incorporate real manufacturing defined data. Every building starts grounded in reality, and within minutes, automation can take you from an LOD 100 conceptual model, conceptual massing, to an LOD 200 schematic design with an engineered structural solution using finite element analysis, and then export schedules of materials which are linked to catalog of real suppliers defined by manufactured components. Imagine this. You are going from the basics of concept to schematic design, but with buildable DFMA components, and you can do it all in minutes and all automated without BIM modelers. That's the magic. So this is where the technology behind all of this and thinking fundamentally diverges from computational design in a traditional sense. Most computational design tools, like Grasshopper and Dynamo, use centralized orchestration. Great for geometry, but the coordinator, that centralized coordinator, becomes a bottleneck as complexity grows. What we've built at Podium is an engine that uses distributed event-driven choreography. Independent configurators respond to events and messages, running parallel and coordinating organically without the need for a central controller. And this shift from orchestration to choreography enables scalability, flexibility, and cross-domain integration. Multidisciplinary coordination happens concurrently. It happens automated, and every time coordination happens, the model enriches as more information is generated. Product catalogs, costs, lead times, manufacturing, all of this becomes primary data instead of being geometry first. The result is a fully coordinated, buildable, and costed solution in weeks rather than minutes. And for each part of the building we want to configure, we have an execution context, which allows us to understand the flow of decisions and actions taken by design agents throughout the design automation. So with this view, what you're seeing is a very granular look at how specific behavior taken by a design agent and what is the consequence. How do we actually turn those decisions, that decision-making engine, into a buildable design? And we can take conceptual mass and in moments have schematic design using an engineered solution. Not a guess, not a probability, but doing the real work that a structural engineer would have done. We want to reduce, if we want to reduce rework, the answer isn't really in a process that results in a better and faster drawing. It's in embedding engineering intelligence into the design process itself. And so by embedding real engineering logic, material properties, supplier products within this framework of architectural design intent, design agents configure both structural and MEP systems automatically, sizing plant rooms, allocating risers, routing services dynamically, checking against architectural layouts and structural zones, all in real time. And this result is a coordinated engineering solution that integrates architecture, structure, and MEPF. It's buildable, it's costed, it's manufacturable, and it's delivered in the time that it used to take to produce a schematic drawing itself. So this isn't just a vision of the future. It's real working software, which is already being used by property developers and design teams today. And by moving beyond that fallacy that Revit documentation equals BIM, and instead of codifying instead we're trying to codify the how of construction and design. We can turn BIM into a true asset for engineered, buildable solutions that really deliver certainty, economies of scale, and reduced rework. And many of you might think AI and automation will try and replace architects and engineers, but they're not. The goal is to encode the best practices into tools that scale, to act as a co-pilot, freeing you to focus on higher value work. So with that, I'm going to hand over to Vitaly at Plan Radar, who's going to show you how data is captured and managed in construction, followed by Tane from Arth Design and Build, who will demonstrate how well-authored data carried forward can be exploited through operations and maintenance. And we'll show you how this golden thread of data can inform construction and lifecycle operation of a building. Thank you very much.
A big thank you, Mr. Kukusami. And with that, we segue very nice